our excuse today is because we have two very distinguished colleagues and friends to, I think, to be with us. Professor Smits from Princeton, Sanjiva Lilly from Stanford. Okay, they come here for a couple of days, and so I think it would be a very good reason for us to get together and to learn from each other a little bit. Of course, I don't think you need me to go through the CV to take up the whole time. Okay. Suffice to say, we have two very distinguished researchers, scholars. I think Lex has done a lot of work in experimental mechanics, and Sanjiva, of course, has done a lot of work from the computational modeling viewpoint. And also, we have invited a few colleagues from HKUST and PolyU to give some sample presentation about our own work. So hopefully with this, we have a good informal, friendly, I think, gathering so we can get to know each other a little more. Okay. And the whole session is extremely informal, and let's make that worthwhile. So, and if you feel tired, walk around, it's okay. Okay. We just showed our guests the fantastic building surrounding here. But let's try to get something out of this. Okay, so with that, I don't think I need to go through any more detail. Let's welcome Professor Smits first.
Oh, thank you. It's obviously a great pleasure to be here today, and it's a very kind invitation from Professor Wei Shi that we are here. And I love Hong Kong, so of course I would come for any excuse to come to Hong Kong. And especially to be in a location like this. I don't know how you people ever get anything work done, because the temptation would be to stare outside the window and look at the islands and the water. So it's an absolutely gorgeous setting. So thank you again for the invitation, and I would like to talk about some of the experimental results that we have obtained in very high Reynolds number flows, and to sort of try to tell you about some of the challenges and some of the interesting results that have come out of this, and rather I think it's a nice story, because high Reynolds number flows is something that we have always tried to examine, because lots of things in our toolbox of turbulence are only valid at very high Reynolds numbers. And so when you look at lower Reynolds number results, sometimes the whole story is not clear. And as I hope to show, is that when you go to very high Reynolds numbers, actually the story becomes a lot clearer. So I do experimental work. That means that we can only measure certain things under certain conditions. But these are the two main facilities that I will be talking about. I'm sorry if I'm blocking this one, but probably it's as easy to look at this one. But this green thing on the right is a pipe flow experiment, and the blue thing is a boundary layer tunnel. And the only thing that's special about them is that they use compressed air as the working fluid, and that allows us to get very high Reynolds numbers. Apart from that, everything else becomes more difficult, because our experiment is now inside this pressure vessel, and exactly what we can measure and how we can measure it become the real challenge. So we all know what Reynolds number is. Of course, it's the ratio of the inertia force to the viscous force in the Navier-Stokes equation. But I also like to think of it in terms of turbulence, where we think of it as representing to some interpretation as the ratio of the largest eddies of turbulence to the smallest eddies of turbulence. So that L, the length scale, becomes a characteristic length scale of the large eddies, and nu over U becomes the small length scale for the smallest eddies. So in boundary layers and all kinds of wall-bounded flows, we would typically choose the large length scale, delta, to be either the boundary layer thickness or the radius of the pipe, some characteristic flow scale, large flow scale. And the smallest eddy size is then represented by the viscous length scale, nu over U tau, where u tau is the velocity scale based on the wall shear. Nu over u tau is of the order of the Kolmogorov length scale. It's probably only a factor of 2 or 3 different near the wall. So it really does represent the smallest eddies that are in the flow. So this Reynolds number, Re tau, is the characteristic turbulence Reynolds number for a wall-bounded flow. And I'll just show you the 2 pictures of boundary layers. On the left you see an Re tau of about 150, and on the right you see one of 2000. And I hope you can see that just from this picture that the ratio of the large scales to the small scales is increasing as we go from left to right. Big eddies, but the small scales are not very small at these low Reynolds numbers. But over here, perhaps you can see there's more of fine-grained turbulence representing the presence of smaller scales. So really just by looking at a turbulent flow, you can estimate its Reynolds number because you'll see large scales and small scales. The ratio of those two is a measure of the Reynolds number of the turbulence. Now this is a 2000, but we're really interested in values of the order of 100,000 or 1 million, representative of large-scale flows, such as flows over a vehicle like an aeroplane or a submarine or a ship, or in the atmospheric boundary layer, or even on things like very large wind turbines. So obviously when things get very large, the Reynolds number increases, and now we have this huge range of scales to deal with. And as I said before, most theories of turbulence really assume that the Reynolds number is sufficiently high. And whatever that sufficiently high means is hard to know unless you can look at a large range of Reynolds numbers and start to see when things become asymptotically large. So that was the aim of these experiments, is to try to get to very high Reynolds numbers. And in this pipe flow experiment, for example, inside that pressure vessel, there's a long pipe flow, about 200 diameters long. And you can see the Reynolds numbers, at least for the turbulence measurements. We can go higher than this, but it becomes very difficult to measure turbulence at these very high Reynolds numbers because the small scales are so small. But for the turbulence measurements, we can cover something like 2,000 to about 100,000, which is not 1 million, but it's getting there. The other experiment is really just a regular boundary layer. Inside here, although it looks like a pipe, it's just a circular wind tunnel. Inside there we put a flat plate, and then we can measure the turbulence on the turbulent boundary layer. And we can't get quite as high on the Re tau values, but it covers a similar range. So these values are the highest, I think, that have been achieved in a laboratory. Most, even very large wind tunnels, have trouble getting this number up above 20,000. And we have a nice comparison now between pipe and boundary layer flows. So probably most of you know this, so I'll go through this quickly. We have this classic scaling argument in a wall-bounded flow, that in the region near the wall, and again here's a boundary layer, flow from left to right, velocity profile plotted in the sort of engineering way. Very strong velocity gradients at the wall because of the no-slip condition. So at the wall, viscous effects are going to be important, and therefore it must be included in the scaling argument. But when we move away from the wall, the velocity gradients are small, viscosity is unlikely to be important, and so we have an inner and an outer argument. The inner scale, the velocity scale, is this friction velocity again, u tau, based on the wall shear. The appropriate length scale is this viscous length scale, nu over u tau. And so we normalize our velocities and our distance from the wall in terms of these velocity and length scales. And these are now the similarity variables for the inner flow, where viscosity is important. And then for the outer flow, we typically use the same velocity scale. You can argue otherwise, but it's fine to do that, especially at high Reynolds numbers. And so we normalize the velocity defect now from the free stream to someplace in the layer by the u-tau. And we normalize the distance not by the inner length scale, but by the outer length scale, which is representative of the size of the flow. So we have an inner region, this yellow border thing, and an outer region, which is this red thing. For some, if the Reynolds number is large enough, which means the ratio of this to that is large enough, right? That's our friction Reynolds number, then there could be a region where both scalings are true at the same time. So we have inner and outer similarity and a region of overlap where that might be true at the same time. So we have the inner scaling and an outer scaling, and I'm showing the velocity profile in two ways. This is the sort of engineering linear plot, and the reason, of course, I'm showing a semi-logarithmic plot is because in this overlap region we would expect to see a logarithmic variation of the velocity. So the velocity depends logarithmically on y plus, which is this y u-tau over nu, the non-dimensional distance from the wall. So it obviously, if we compare the experiment to the theory, we find indeed there is a region of semi-logarithmic variation, which is shown on the left in the linear plot and on the right in this semi-log plot. So this is a sort of scaling argument that we would expect to see, and if we go to the pipe flow now, where we have this very large range of Reynolds numbers, we can see that as we go up in Reynolds number, this is a low Reynolds number, here is the center line of the pipe, so that's why the velocity starts to decrease again on the other side. But as we go up in Reynolds number, this wake region just continues to go up, and we see this longer and longer region of what looks like a logarithmic variation. But in fact, there is a small difference near the wall that if we look at it in more detail, and these points are representative of the experimental uncertainty, so we tend to believe this result, is that actually there is a region near the wall that doesn't follow a logarithmic behavior. There's a small deviation. It's not very significant, except that it is telling you something, that you haven't achieved a high enough Reynolds number to really see the true logarithmic law appear. See, because Reynolds number increases as we go out here, right? Because this is just y over nu over the viscous length scale. So out here somewhere is r plus or delta plus, and so you only see this region here if you have a sufficiently large Reynolds number. So for small Reynolds numbers, you only see this little bit, and then you can see that there is it doesn't look like a log law. It looks like a power law region, and it looks like the constants might be dependent on Reynolds number. They're not, but you have to go to a high enough Reynolds number to see that, and it turns out that it's considerably higher than most people would say, because these results say that the log law starts at about 800, and most people would have thought that it would have started at somewhere around 50. That's a big difference. As I said, I don't want to make too much of that, but it tells you something, that something is going on at parallel scaling. But really we're interested in the turbulence. So to measure the turbulence, we use typically hot wire anemometry. It's still the most accurate way of measuring turbulence. It gives you a time signal, you can look at the spectrum. It has a lot of attractive features to it, except of course it only measures one component at one point, unless you go to elaborate other configurations. But still, so it's a thermal device, so that we have these fine wire filament on the end of our probe. It's in a feedback circuit that tries to keep the resistance of this probe constant. Its temperature, in other words, is kept constant by this feedback circuit. And what happens as the flow velocity varies, the heat transfer from this probe changes with time, and therefore you have to feed more current to it to keep the temperature constant. So you can monitor that voltage, and through a highly nonlinear arrangement, it tells you something about the velocity fluctuation. It's a horrible instrument, but it's the best we've got. And we've spent 100 years or so trying to understand it, and so we kind of know most of the pitfalls, but it's still the best thing around. So this is what we do, but there are two problems with this, apart from the first 2 points there, is that clearly the size of the probe tells you what the smallest eddy is that you can measure. Because if the eddies are smaller than the probe length, then obviously they're going to be filtered out, and their energy will not be contributing to the total. So you're doing a spatial filtering on the signal. And the other issue that's important is that we have these end conduction issues, so that the temperature is not uniform along the length of the wire. There is conduction into the supports, and that changes your Bode plot, your frequency response diagram. So to get rid of that effect, you really need the wire to be long. So we have this conflicting requirement on these probes, is that you want to make them really small to avoid spatial filtering, but you also have to keep them long to avoid end conduction effects. So there's a limit to what these things can do for you. And so we decided that the only way to measure turbulence accurately in our facilities was to have to develop our own instrumentation. And so we developed these, what we call Nano-Scale thermal anemometry probes, NSTAP, and we use semiconductor manufacturing techniques to make them. All we're really doing is taking the hot wire geometry and trying to make it really, really small. And so we can keep the length to diameter, or the effective diameter ratio, high, and at the same time physically shrink the size so we can measure the smallest eddies. Right? And that's our problem, because let's say we have a pipe flow, it has a fixed size, and so as we increase the Reynolds number, remember R U tau over nu, that as the Reynolds number gets larger, the biggest eddies stay the same because they're fixed by the geometry, but the smallest eddies get smaller and smaller and smaller and smaller. So as the Reynolds number increases, we filter more and more of the small scales for a fixed probe size. So that was our problem, right? So Margaret Valakuvi did a remarkable job in making these probes and developing especially this technique to make these probes aerodynamic as well as small, because again, you can't have a big probe, relative big probe sitting in the probe. In the flow, it's going to interfere with the flow itself. So we tried to make these things as aerodynamically shaped as possible, and so it ended up looking a bit like the Starship Enterprise. But that's okay. It's rather attractive. Don't you think it looks like a spaceship landing on some planet made of cheese? So the sensitive element is right there. It's at the tip of this thing. This is an early picture of a 60 micron probe. It's actually a thin ribbon. It's not circular. It's a thin ribbon. But it has a very small thermal mass. So it has a very good frequency response as well. Here is a 30 micron version. So again, there's the sensitive element. And of course, you don't just make a probe and put it in the flow and declare success. We spent a long time checking these probes against regular hot wires where they should give the same answer, and we convinced ourselves that it really was behaving as it should. So that allowed us to look at the turbulent fluctuations. Then this is in the pipe flow, and this is now plotted again semi-logarithmically in y plus, so this non-dimensional wall distance, and we have non-dimensionalized the velocity fluctuations. Remember, I'm only measuring one component, the streamwise component, and I'm taking the variance, the mean square, time averaging it, and non-dimensionalizing it with u tau squared. Okay. So this is a representation of here. You can see this is covering a huge range of distances from something like a y plus of 2 all the way out to a y plus of almost 100,000. So this is really close to the wall, right, compared to that. And then what you'll see as the Reynolds number changes, we go out in this direction. Two things happen. One is that we see a peak in turbulence intensity near the wall. This is the region where there is the maximum production in turbulence, the maximum dissipation, the maximum magnitude of the variations. Really close to the wall. You can see it's sitting at a y plus of about 10. At the highest Reynolds number, that is 1/10,000th of the radius. So this is really a very small region near the wall. As we go out, this is a low Reynolds number case, then we increase the Reynolds number to this highest Reynolds number case, which is like 100,000, and we see the development of an outer peak in the turbulence intensity. This you would not see at lower Reynolds numbers. If you were stopped at this blue case, which is something like 10,000 in RE tau, you would not see this peak. But if you go to higher Reynolds numbers, you can see it gradually develop. So this is interesting, especially because this peak looks like it's saturating. It doesn't continue to increase with Reynolds number, but this peak is increasing with Reynolds number. So you could speculate that at infinity, that outer peak is going to be larger than the inner peak, and now all the production and everything, all the dissipation is really taken over by the integral over the outer flow rather than this small region near the wall.
Right.
So character changes.
In physical terms, what is the inner Nano-Scale roughly?
In the analog scale, well, if you bear in mind that the radius of the pipe is about 60 millimeters, so when we go 1/10,000th of that, we're now talking about, to here it's about 6 microns at the highest Reynolds number. Yeah. So it's very hard to get the probe that close to the wall. In fact,
microns still is very thin.
yeah. In fact, the closest we ever got for this was actually about 12 microns. And that was completely accidentally because we meant to put it at about 20 to be safe. And someone slipped. And then it was at 12. And we said, don't touch it. So the other part about this is that if you just now look at it in the other coordinate system, this is now the outer scale, right? So it's the similarity variable for the outer region. And if we just take away all the points where y plus was less than 100, because that's all near wall region, now we're looking at the outer region, you can see that an interesting trend with Reynolds number is that this level is going out in a very orderly way, and what it's doing is it's revealing this semi-logarithmic region now in the turbulence intensity, which is a really nice result. This kind of relationship, this semi-logarithmic behavior on the turbulence intensity, was first anticipated by Townsend in 1976 on the basis of an attached eddy argument. A very simple argument that says the turbulence has to scale with the distance from the wall. If you go through that and make some inspired Townsend kind of arguments, you would predict a semi-logarithmic variation in the turbulence intensity. Tony Perry and I did a different argument based on a spectral overlap argument, and I'll come back to that. But both of these investigators predicted this result. These constants, the best that Tony did was an estimate of about 0.8 on that exponent, on that constant, because he didn't have access to the high Reynolds number data that we have. So I think that we were really the first to show it, that it really does exist, and to actually get the right constant for this log law. Where does it sit with respect to the mean flow? Well, this is the interesting part. I'll just fill in the blanks here. Okay. Let me describe what's happening. We're now again back to a semi-logarithmic plot using the inner coordinate, and we're plotting the velocity. The mean velocity is this profile, the red dots, and you can see where I had drawn the logarithmic variation in the mean velocity before, from about here to about there. And now I've also plotted the turbulence intensity profile for the highest Reynolds number, and you can see the logarithmic variation of that, and that they occupy the same physical region. So this is also a wonderful result, because we've always expected that there would be a region in these wall-bounded flows where the flow is essentially independent of the inner scale and the outer scale. It's the overlap region where both scalings hold, therefore neither can hold. And so it's a region where things scale as 1 over the distance from the wall, which gives you the logarithmic variation, both in the turbulence and the mean velocity. So this, I hope, would make every person who's interested in wall-bounded turbulence feel good, because we expected it, but it's very hard to get the evidence because it only really resides at these very high Reynolds numbers. So we did the same thing in the boundary layer, and we see some very similar behaviour in the boundary layer. You see the turbulence intensities again. We see a peak that seems to saturate. There's the emergence of an outer peak, but the trouble is with boundary layers is that in pipe flows you can get the velocity scale u tau very accurately, because it's just the wall friction. You can get it from the pressure drop down the pipe. It's very easy, nice, accurate way of getting u tau. In a boundary layer, it's very, very difficult to get a good estimate of what u tau is. So this is our best guess. So we really need better results on our scaling to be able to make this conclusive. But it looks pretty good. Right? It seems to follow the same trends that we see in the pipe flow. And then when we look at the same kind of cross plot of the mean velocity and the turbulence intensity, we see again this region here where both the log laws hold over the same physical region of space. So it makes you feel good too. I skipped over this region here. That's the region where in the mean velocity we saw a deviation from the log law, that small deviation, that power law deviation, which I said wasn't very important, but it sort of shows up here too. And it represents the kind of transition from this flow that is independent of viscosity to one that is starting to depend on viscosity. And that this kind of shoulder region between the two scaling behaviours shows up here as a deviation from the log law. Small deviation, it's more apparent in the turbulence. And it really is the meso layer. And people have again supposed the presence of this meso layer earlier than us. But it seems like we're able to now define properly where that sits. And that's another thing. So we've added a layer to our understanding of wall-bounded flows. We have the near wall region, a meso layer, a log layer, and then the outer wake region. So, is it universal for the turbulence? We saw it in the pipe flow, we saw it in the boundary layer. It's also good that other people have seen it. That means that they're almost as good as us, right? But this is results from an atmospheric boundary layer in the SL test facility in Utah. This is our results from the Superppe. This is from the large cavitation channel in Tennessee, which is this gigantic water channel that the Navy operates. And this is from the Melbourne boundary layer tunnel, because as I should have mentioned, we've been working with Ivan Marusik for some years on these problems, and we try to keep very close touch. This is just a regular wind tunnel, but it's very large, very long, so they can develop high Reynolds number, thick boundary layers. So they can measure things more accurately than we can. And it's always good to see that they get similar results. So we see this log law in different places, and the nice thing is that the constant stays the same. This slope here is the same in the atmospheric boundary layer, in the pipe flow, and in these boundary layer flows. So it may be universal. And Ivan and I are trying to get people to call that the Townsend-Perry constant, because they were the people who really came up with that. You can see it everywhere now. I mean, we've seen it in a smooth pipe, we've seen it in a rough pipe. It shows up in not just the second order moments of the turbulence, but higher order or higher even order moments, the fourth, the sixth, the eighth, all show this logarithmic dependence. So what about spectra? Well, I said that there was a spectral argument that was underlying the log law in turbulence, and I just want to spend a few minutes on that. This is our usual representation of the spectrum, right? Log. This is just a one-dimensional frequency spectrum, really, but it's been turned into a wave number spectrum by using Taylor's hypothesis. And so you can do a spectral overlap arguments to say if you take the intermediate scales, should depend upon the distance from the wall and U tau, and then you take the high wave number end, where it should be viscosity and dissipation, and if you do an overlap argument there, you can predict the minus 5/3 law, which of course is one of the cornerstones of turbulence theory, the Kolmogorov minus 5/3 spectrum region. And so we can compare that to our data, and we see that this k to the minus 5/3 region, it's sort of there, but it really doesn't fit very well. There's a noticeable deviation from minus 5/3 slope, and it really looks more like a minus 1.5 slope. You can just see that by eye, that that's not a bad fit to that data. And that's also not new, that there might be deviations from the Kolmogorov minus 5/3 region. Depends on the Reynolds number. And Milaski and Warhoff, Gamard and George have postulated some deviation from 5/3. This mu that depends on 1 over the logarithm of Reynolds number. And if you plot the data, kind of agrees, the low Reynolds number data. And this is where our data sits out there. And you can see that their postulate for this exponent certainly it seems to agree with our data. We lie in this Reynolds number range, and we get about 1.5, which is close to what they would suggest for this Reynolds number range. But you see, the problem, to get to minus 5/3, we have to be somewhere over in Hong Kong, right? Because even at this the RE lambda that's based on the Taylor microscope, at 1,000, you're still nowhere close to minus 5/3. So sometimes an infinite Reynolds number really is very large. Now the other argument that you can make, this is Tony Perry and Chris Abel and Henbest and Chong, said, well, there's another overlap region possibly at high Reynolds number, one between the very lowest wave numbers that should scale on the size of the flow, and this intermediate wave number range that scales with the distance from the wall. Sufficiently high Reynolds number, they can be separated by orders of magnitude, and there could be an overlap region here, and in that overlap region, you would predict a k to the minus 1 region. And so we look at our data, and sometimes it does and sometimes it doesn't. The trouble is with looking at slopes is that if you have a curve like that, there's always one point that has the right slope. So you're looking for an extended region of this minus 1 region. And so we were looking for this region in minus 1. It had been seen earlier on by Nichols. It shows up as a kind of plateau region in this pre-multiplied form. So in other words, if you multiply the spectrum by the wave number, then the slope of that logarithmic law becomes the plateau region here. So if you're looking for minus 1, it's going to show up as a plateau in this pre-multiplied form. And you see there's a small region there that seems to behave the right way. The trouble is that value, the height of that plateau should be equal to the constant in the log law. You can see here it's around 0.8 and it should be 1.25. So that doesn't seem right. And when we look at our data, this is at a low Reynolds number, 5,000. We have the boundary layer on the left, the pipe on the right. What should happen is that this is an overlap argument, so you have to find a region that scales both with the outer flow and the inner flow at the same time. And what we see is when we plot it in this, in the Y scaling, we see it sort of collapses over here, sort of collapses over here. When we do the delta scaling, it doesn't really collapse anywhere here, maybe a little bit over there. So, okay, so we're not at a high enough Reynolds number. So let's go to a higher Reynolds number. And now we see a better collapse. It collapses in Y here, and it collapses in delta there. Y here, delta there. That looks good. The trouble is they don't collapse in the same region. There's no overlap. So the overlap argument doesn't work because there is no overlap. And again, you need a high Reynolds number range to be able to say whether this overlap region exists or not. So it was a great argument, really physically based, but it's not supported by the data. So we don't see a k to the minus 1 overlap region, but we do see a log law. So what happened? Right? The overlap argument gives you the log law. We see the log law, but we don't see the overlap argument. So something's different. And this is where we get a little bit into the details. When we do look at the spectrum now over all Reynolds numbers and all positions from the wall. So here's our turbulence profile for a given Reynolds number. And this is the spectrum at that point there, the blue point. So as we step through this, and I'm slavishly copying Nick Hutchins here, who does this very nicely, we can see that now the spectral plot is being built up by these different points along in the boundary layer. So here we are moving away from the wall, and we see a region, a peak in the spectrum near the wall, and we see a peak in the spectrum away from the wall. This inner region basically stays the same no matter what the Reynolds number is. But this thing starts to develop with increasing Reynolds number, and it's been tied to the very large scale motions in turbulent boundary layers, if you know what they look like. So that's what the spectrum looks like, and now we can turn it into a contour plot, like that. so that we're looking down on this thing now, and we've just got the magnitude as these colours. And so here's the inner spectral peak, there is the outer spectral peak, and now we can see what happens as the Reynolds number changes. Right? And we're plotting y over delta here, the distance from the wall, and the wave number here. And then just to really confuse things is we usually plot this in terms of the other way around, wavelength, so that the wavelength is increasing in this direction. But here is the inner spectral peak, there's the outer spectral peak. This is a Reynolds number of 5,000. And so the question is, what happens as you increase the Reynolds number? Well, there we go. As we increase the Reynolds number, the inner spectral peak stays there, but it's we can no longer measure it because it's so close to the wall that we can't get the probe closest. But we can track this outer spectral peak, and we find that it sits here. Earlier predictions have given that it starts to move. At low Reynolds number, they're all together. These predictions say that it should move outwards. It doesn't in our data, it just sort of sits there. And in fact, if we connect it to the turbulence profiles and the mean velocity profiles, remember this is the cross plot, we see that the outer spectral peak really marks the beginning of this log region. Right? There. So it seems to be fixed in terms of this y plus. In non-dimensional units, it's sitting at the same location near the wall, and it marks the beginning of the logarithmic variation in the turbulence. So how does this relate to an overlap argument? Well, oh, by the way, we do this in the pipe also. That was in the boundary layer. We see this in the pipe. We see the same thing. The movement, the outer spectral peak essentially stays where it is, and it marks the beginning of the log law in turbulence. So it turns out you don't need an overlap argument to get the log law in turbulence. If the turbulence intensity is essentially the integral under the spectrum, of course, right? If you look at the energy containing range, if that range is essentially defined by a limit that is fixed in delta and a limit that is fixed in y, and you have a plateau region, in other words, A1 over K1 things are varying as 1 over y, you are going to get a log law. So you need three things. You need a plateau region in the pre-multiplied spectrum, and you need the lower limit to be set by delta and the upper limit to be set at a fixed value of y. And it turns out that that's actually true in the spectrum. Now this is where Nichols et al. Found a -1 region. They were looking for this because of an overlap argument. They found that. And this is what we find, is that it really sits out there. So it occupies a much larger region, and there is an overlap. So we're not contradicting Nichols's results. It's just that they saw one piece of it, and now we've seen more of it. And there could be more out there. But the nice thing is that you don't need this overlap argument. The spectrum somehow behaves the way it ought to give you the log law. So that's where I'll stop. Just to summarize, we've seen some interesting trends as with the increasing Reynolds number. I think the most heartening aspect of this is that our theories weren't bad. They really, a lot of smart people did a lot of good thinking about what should happen at large Reynolds numbers. And we see some of it because we can go to these very high Reynolds numbers. We see log laws in the turbulence. We see some of the arguments weren't right, but the predicted result still holds. And there are, of course, other parts of this where we still need much higher Reynolds numbers. Like the -5/3 region is something that you're only going to see at extremely high Reynolds numbers. The -1 region is interesting because we see it developing in these high Reynolds number flows in almost the wrong place, but it explains why we can never see this at lower Reynolds numbers, but people in atmospheric boundary layers, for example, have seen the -1 region. And so there's the difference. It's just a question of Reynolds number. So it's kind of nice to see some of these things fall into place. And that's all I wanted to say. Thank you very much.
Professor Smits, very interesting talk, impressive high Reynolds number testing facility and results. You show us the Nano-Scale testing probe to measure small eddies at high Reynolds number. And you mentioned about the calibration with the traditional hot wire. I just wonder, because you designed this Nano-Scale probe to measure the small eddies, so how did you calibrate with the traditional hot wire, which cannot provide you the data on the small eddies?
Yeah.
So I just wonder how.
No, that's absolutely a fair question, because we can only cross-check them in a flow where they both give the right answer. So that either means that the flow has to be a low Reynolds number, because then both probes give adequate spatial resolution, or you need to have a flow that is big. Because if it's big, then the small scales are still reasonable, and then you can still measure at high Reynolds number and compare the two. And we did the first part. We compared them where the Reynolds numbers were relatively low, but we knew they should agree. And then we've worked with other people like Eberhard Bodenschatz at Göttingen, and with Ivan Marusik at Melbourne, where they have these larger scale flows but still very high Reynolds numbers. And now we can compare them, and we can start to see where they begin to deviate from each other. So yeah, it's a non-trivial thing to say, I have a new probe and it works. Well, prove it, right? Prove it.
And one more question. What about the response function of this Nano-Scale probe?
Yeah.
Does it work properly? Or?
Yeah, again, there was some very nice work. Nick Hutchins and Jason Monty from Melbourne came to Princeton, and the nice thing about the facility that we have is that you can change the Reynolds number different ways. You can change the Reynolds number by pressure or by changing the velocity. And so you can now look at the response of the wire over a range of velocities at a fixed Reynolds number. And so now you can see what happens as you change the velocity, what does the frequency response function looks like. And so that's been published in Experiments in Fluids. So again, that was a lovely study, but he did it, he thought of it. And so we build confidence in the probe and how it functions. Yeah.
Thank you.
I still wish it would be smaller.
In the nanowire, this hot wire, right? So what's the smallest size you can fabricate, and then how close to the wall you can measure?
Yeah. The smaller, well, we've made smaller ones since. The smallest ones we've used in these experiments were 30 micron long. They're about 2 micron in the stream direction and about 100 nanometers thick. So then you have to take this thing and, you know, the probe has some bulk, right? Because it's supporting this wire. Then you have to get it close to the wall, and you have to know how far away you are. So we have an optical microscope to tell us to within about a micron or maybe 2 micron to where it is. And then, you know, if you're talking about moving a small, delicate element next to a solid surface, it's a little tricky. So you just, yeah. But you can do it. It just takes time. But all these results, all the pipe flow results were taken with one probe. And all the boundary layer data were taken with one probe. They're actually quite robust.
How smooth is the surface?
Well, it depends on the Reynolds number. For the pipe flow results, the maximum K plus value at the highest Reynolds number for the turbulence is like 0.1. So it's pretty good. It'd be more like 0.2, sorry. For the boundary layer data, it's a little better.
Because when you use this, do you still have to follow the normal routine using the standard hardware wait until you set it down afterwards, calibrate the same and so on?
Yeah, we calibrate before and afterwards, yeah. Yeah, it's you can't get away from that. But they don't drift very much. No, they don't. They're very good. They actually seem to be more well behaved than regular hot wires, in many respects.
So if you want to increase the Reynolds number, the size of the wire still is the limit.
Yeah.
That's
Yeah, you're still stuck with that. So, Marcus Holdmark, who I work with, he's actually making smaller probes now, of the order of 10 micron. But we have to calibrate them, we have to figure it out, so it's not easy.
I have to say, when I was a student, I was in the same department with Bill Wilmoth. He was doing, at the time, micro probe, and I was happy I was not his student.
Oh, yeah.
So much work.
Oh, yeah. But, the good thing is about these probes is that we make them on a wafer, and if you can make one, you can make 200.
That's right.
So your hardware was calibrated without away from the solid world, right?
Yeah.
But during experiment, your hardware is very close to the world.
Yeah.
World may affect heat transfer. So that
if you get close enough to the wall, then you're going to get some heat transfer effects to the wall. But in fact, these probes are not. They generally run at a slightly lower, considerably lower temperature than the usual hot wires. And, the best estimates we could make on previous experiments like that, it was not an issue. But yeah, it's something that we're aware of. The other thing that happens, of course, if you get really close to the wall, then you might get some convection problems, so Peclet number effects. And again, we tried to stay away from regimes like that.
Still the Nano-Scale hard. So you must spend a lot of tremendous time and effort to develop this. So is it available from the market now, or how much to make one?
Well, you see, we give them away because first of all, if we charge for them, they would be very expensive. And the second thing is that I don't do customer service. We'll give you the probe. We'll tell you how to use it, right? And then it's up to you. Yeah. Don't complain to us. See, so and honestly, it's not a big deal because we make 200 probes at a time. So to give a few probes, now we can't do this on a big scale, but look, there's only about 5-10 groups in the whole world who would be interested in using these probes, so it's not a big deal. Yeah. We can't make any money anyway, so what's the point? Sanjay?
I had a question about the scaling that you were showing for the intensity of U prime.
Yeah.
With increasing Reynolds number, and you made a comment that the outer peak keeps rising in the wall units.
Yeah.
The intensity also keeps rising as scaled by U tau.
Yes.
And so ultimately, at very high Reynolds number, what do you think happens?
Well, essentially the inner region becomes irrelevant.
But what would set the scale for U prime in that limit? When the outer layer is the dominant layer.
Yeah. Well, it's still going to be the friction at the wall. It's going to be the total dissipation in the system, right? I mean, some measure of how hard you're working to produce the turbulence. Right? So, yeah. Dale Pullen gets very excited about this kind of thing.
Right, can you say a few things about the hairpin? You were talking about the inner peak.
Yeah.
And then you, in the beginning, you showed these two pictures of the scale variation.
Yes,
right?
yes.
And then, of course, a lot of these are now later you present a lot based on scaling analysis.
Yeah.
Can you say a little bit more about dynamics in terms of?
Yeah, you know, this is something that we've been looking at in another set of experiments, but essentially that outer peak in the spectrum is associated with the very large scale motions. But of course there is also another peak in the spectrum which is generally associated with the large scale motions. And so what you see is that as you increase the Reynolds number, they essentially scale differently. But what seems to happen, at least in the outer flow, of course, the very large scale motions take over. Now, what we've been doing as well is to look at pipe flow again, but we're using sort of multiple plane stereo PIV to image the large scales themselves. And what we really find, as what Ron Adrian anticipated, is that the very large scale motions are really made up of large scale motions, that, you know, the bulges that are aligned in the streamwise direction. Because we can actually look at these individual events and we see that these large scale motion correlations only last about 1 or 2 radii. And so that's the key, that they're actually made up of large scale motions, all put together in a train. And they have a characteristic grouping size. So yeah, we're trying to relate the spectrum to the structure. It's sometimes not easy because the spectrum is such a crude measure, and that's why we've gone to this stereo PIV, multiple planes, to see the development of these large scale motions. So that's where numerical simulations can be so useful. You know, even if it's a low Reynolds number, I don't think that the connection between the large scale and the very large scale motions is preserved at low Reynolds number. So, yeah.
Very good. Please.
In the boundary layer experiment, in order to have a boundary layer which is not affected by confinement,
Yeah.
you would need the boundary layer to be relatively small compared to the size of the
It is, yeah.
And so as you push Reynolds number, are you able to keep that separation between the boundary layer scale and the
Yeah,
outer scale?
because you know, if we're at a fixed x, so as you increase the velocity, it's going to decrease the boundary layer thickness. So, but we actually spent a lot of time worrying about the circular part of it and whether that would lead to span-wise pressure gradients. And so we actually did an experiment in a regular wind tunnel. We measured the boundary layer, then we put this circular confinement on it, and we satisfied ourselves that everything was fine. So, yeah. None of this has come easy. Okay.
Okay, let's thank you.
Thank you very much.